Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss conductors in electrostatic field and the surface charge and force on a conductor. Let's begin. When a conductor is placed in an electrostatic field, then what happens? Inside the conductor, both electric field and charge will be zero. And the charges reside only at the surface of the conductor. Immediately outside the surface of the conductor, the electric field is perpendicular to its surface, and the potential both sides and the surface of that conductor is constant. These points are happened when a conductor is placed in an electrostatic field. Now let's take an explanations of all these points when that conductor is placed in an electrostatic field. What is conductor? Those materials through which current can easily conduct are said to be conductors, and all the metals are under the category of conductors, and here the free electrons are the charge carriers through which the current flow through that of conductors. Since the free electrons always exist in a conductor, when a conductor is placed in an external electric field, here we take an conductor. When that conductor is placed in an external electric field, this is the external electric field, is created like this. The free electrons always exist in that of conductor, and when that conductor is placed in an external electric field, what happens to that of free electrons? These free electrons experience a force and move in the direction to the opposite to that of applied electric field. This is the applied electric field. This is from positive to negative, but here the free electrons are just opposite to the applied electric field. Here the redistribution of charges takes place on the surface of that of conductor like this. Negative charges are here and the positive charges are there. The charges are redistributed on the surface of the conductor as far as we applied an external electric field from positive to negative. Hence produces induced negative charge at one end and induced positive charge on the other end of that of surface of the conductor. Thus an induced electric field is kept on the conductor whose direction is opposite to the direction of external electric field. Here the induced electric field direction is opposite to the applied external electric field. The final distribution of charges at the surface of the conductor is such that the induced electric field set off due to appearing of induced charges on the surface of the conductor just cancelled with the applied electric field. Therefore, the net electric field inside that of conductor is 0. Here the net electric field is 0. As we say here, inside the conductor electric field will be 0. Now how charge will be 0 here? We can explain it. Further, the electric field at the surface of the conductor or just outside, it can't have tangential component. That's the reason why there will be no such tangential components, because if the electric field had tangential component, it will lead to the flow of the surface current. Hence, when a conductor is placed in an electric field, the electric field lines, or we can say the electric lines of force, will enter or leave the conductor at a right angle to the surface of the conductor. That's the outside the surface of the conductor, the electric field is perpendicular to its surface. That point is explained. Now, since the net electric field inside the conductor is 0, net electric field inside the conductor is 0, this implies that no net charge exists anywhere inside that of conductor. Now, this can be explained by using Gauss law. Let me consider a Gaussian surface inside the conductor as close as possible. Here we take the Gaussian surface inside that of conductor as close as possible to that of surface of that of conductor. Hence, the electric field intensity will be 0 everywhere inside that of conductor. It must be 0 at every point on that of Gaussian surface. Since the electric field inside that of conductor is 0, so as we take the Gaussian surface, here it will be 0. According to Gauss law, the closed surface integration, that is E dot ds, is equal to charge enclosed divided by epsilon naught. As the electric field here will be 0, means there will be no such electric field inside that of conductor. As a result, since electric field will be 0, so Q by epsilon naught is equal to 0, as electric field is 0 inside that of conductor. Therefore, charge will be 0 inside that of conductor. That point is explained. Inside the conductor, charge is 0. Inside the conductor, electric field is 0. Inside the conductor, charge will be 0. Here all these points are explained. Last point, the potential both inside and on the surface of the conductor is constant. How? Look at the expression as E is equal to minus dV by dr. Electric field is the negative of potential gradient. Here electric field will be 0. Inside that of conductor, electric field will be 0. So that is equal to 0. Therefore, its differentiation is 0. So potential will be constant. So V is equal to constant here. That point is explained. The potential both inside and on the surface of the conductor is constant. These points, when that conductor is placed in an electric field, are easily explained in this way. Now, surface charge and force on a conductor. When we consider a charged conductor, note that when we consider a charged conductor, since the total charge resides on the surface of the conductor, in case of charged conductor, the charges are not inside the conductor, but that charges are on the surface of the conductor, and inside that of conductor, charge will be 0, as we discussed here. So because due to the charges are resides on the surface of the conductor, what happened? The similar charges repelled each other, and the charge on any part of the surface of conductor is repelled by the charge on the remaining part of that of surface of the conductor. Since the charges are reside on the surface of the conductor, so the according to the property of charge, similar charges are repelled with each other. And how the repulsion is takes place? The charge on any point of the surface of conductor is repelled by the charge on remaining part of the surface of the conductor. and this repulsion between the charge of like sign on the surface of the conductor causes a charge conductor which experience a mechanical force. That charge conductors, due to that of repulsion, that execute a mechanical force, and we have to calculate the magnitude of this mechanical force. Means we have to calculate the force per unit area, on that of conductor. How to calculate? Let we consider xy the surface of the charge conductor. This is the surface of charge conductor that placed in free space. Means here permittivity of that of free space with the epsilon naught. So we write here the things like xy surface of charge conductor, that the surface of charge conductor placed in free space, sigma is the surface charge density, means charge per surface area of that of conductor. Let here consider a small area element. Here we consider a small area element named as AB. Small area element of the conductor xy, and let the area of this area element, is dA. dA be the area of this area element AB. AB be the small area element and its area will be dA. Here let P be the point just outside the area element. So according to Coulomb's law, we can calculate the electric field intensity at point P due to that conductor. Now the electric field intensity according to Coulomb's law, according to definition of electric field, the electric field intensity that is according to definition, or we can say that is according to Coulomb's law. According to Coulomb's law of electric field, the electric field intensity at point P due to that conductor, that is E is equal to sigma by epsilon naught. Sigma is the surface charge density, epsilon naught that is the permittivity of free space, and the direction of that of electric field is normal to the surface of the conductor. So here the electric field intensity at point P due to that charge conductor is given as sigma by epsilon naught, and its direction is normal to that of surface of the conductor, and that electric field is created due to two types of charge distribution. Means here the electric field intensity may be assumed partly due to the charge on AB and partly due to the charge on that of conductor XY. Due to these two types of charge distribution, we calculate the electric field intensity at point P. So here we can take E1, let E1 is the electric field intensity at point P due to charge on element AB, due to charge on element AB is E1, and E2 with the electric field intensity at point P due to the charge on remaining portion of the surface. E1 due to the element AB, and next E2 is the another section of that of charge conductor. So the electric field intensity at point P is due to E1, two types of charge distributions in this way, two types of electric field intensity. So E1 due to that element charge, and E2 due to the remaining portion of that of conductor, electric field intensity at point P, and that direction is normal to that of surface. So here that electric field intensity, we can say then that electric field intensity at point P, that is E is equal to E1 plus E2, which is equal to sigma by epsilon naught, We take equation number 1. Now consider a point P dash. Consider a point P dash just near the element AB inside the conductor. Then what happened? Then the electric field intensity at point P dash also be assumed partly due to the charge on that of element AB and partly due to the remaining charge. So the electric field intensity E1 and point P dash due to the element AB is of the same magnitude, because P and P dash are situated very close to that of element AB but in opposite direction. So here due to that element AB, the electric field intensity at point P dash will be how much? E1 or E1 dash is exactly same and opposite to that of E1. Here the direction of E1 At point P, the electric field intensity due to that element charge AP. And the magnitude of electric field intensity E2 due to the charge of that of remaining portion at that of point P dash are the same, but also the direction is same as that of E2. Means here the direction of E2 is here. Then the net electric field intensity as the resultant electric field intensity at point P dash will be E2 minus E1. So we can write here the resultant electric field at point P dash is equal to, that is E2 minus E1 as shown in that figure as we explained. Look here, inside that of conductor, here P dash is the point which is inside that of conductor. Inside that of conductor, the electric field intensity is 0. So as therefore E2 minus E1 is equal to 0, as electric field intensity is 0 inside the conductor. Inside the conductor, the electric field intensity is 0. Therefore E2 is equal to E1. These two electric field intensities will be same. Now putting this value in equation 1. Now putting this value in equation 1, we get, in place of E1 we can substitute E2. Therefore two E2 is equal to sigma by epsilon naught, or E2 is equal to sigma by 2 epsilon naught. Here what is E2? E2 is the electric field intensity on that of line element AB due to the charge on the remaining portion of that of surface. Here E2 is equal to sigma by 2 epsilon naught. Since the surface charge density is sigma, therefore the surface charge density will be charge on element AB divided by area of that of element AB, area of element AB. Surface charge density sigma is equal to charge on element AB, let Q be the charge, and area of that of element AB we consider A. That is dA. dA be the area element AB. Here we take dA. Therefore charge is equal to Q is equal to sigma into dA. Charge on that of element AB, Q is equal to sigma into dA. So the force on that of element AB, therefore force on element AB is equal to electric field intensity E2 into charge E is equal to F by Q, so F is equal to EQ, that is E2. Therefore at the force on element AB, that is F is equal to E2Q. So F is equal to, in place of E2 we substitute sigma by 2 epsilon naught place of Q, that is sigma into dA. That result F is equal to sigma square divided by 2 epsilon naught dA, that is the force. But our task is to find out the result of force per unit area on the conductor. So force per unit area, thus mechanical force per unit area, thus mechanical force per unit area is equal to F divided by dA. Therefore force per unit area F divided by dA is equal to force, that is sigma square divided by 2 epsilon naught dA whole divided by dA. dA cancel out here. F divided by dA is equal to sigma square divided by 2 epsilon naught. This force per unit area, this force acts normal to the surface of the conductor. From that of expression, as E is equal to sigma by epsilon naught, as here we take E is equal to sigma by epsilon naught. So here sigma is equal to E into epsilon naught, that expression can be put here. In place of sigma we substitute E into epsilon naught. So F by dA, force per unit area, here we introduce E into epsilon naught. So E square epsilon naught square divided by 2 epsilon naught. So final result, force per unit area is equal to half epsilon naught E square, half epsilon naught E square, the force per unit area. Hence the mechanical force per unit area acting on the surface of a charged conductor will be half of epsilon naught into E square. So with the help of this video lecture we understand when a conductor is placed in an electrostatic field, then what happened. These are the points and the explanations of these points, and the concept of surface charge and force on a conductor. Here we have to calculate force per unit area, and we take the conductor and calculating the force per unit area, mechanical force per unit area, by taking electric field intensity, then taking the point P and P dash. Simple mathematics. So force per unit area, that is half epsilon naught E square. Epsilon naught permitted of that of free space, E the electric field intensity. So with this useful and informative notes, let me wind up the session. Thank you.